Welcome to Quantum, where we explore the deep intersections of mathematical, theoretical, and philosophical physics. Today's lecture delves into one of the most fascinating discoveries in condensed matter physics, the quantum Hall effect. This phenomenon intertwines quantum mechanics, topology, and non-commutative geometry, revealing profound insights into the structure of physical reality. First discovered in the 1980s, the quantum Hall effect demonstrated something unexpected. Electrical conductivity becomes precisely quantized when electrons move in a strong magnetic field. Unlike conventional phase transitions, this quantization is remarkably stable, resisting material imperfections and experimental noise. Its robustness suggests that it is not just a property of individual electrons, but a global, topological effect. Beyond its significance in condensed matter physics, the quantum Hall effect has deep theoretical connections, ranging from the physics of black holes and holography to the fundamental nature of entanglement and gauge theories. The classical Hall effect and charge transport. To fully grasp the quantum Hall effect, we begin with its classical counterpart, the Hall effect, first observed by Edwin Hall in 1879. Imagine a thin metal strip with an electric current flowing in one direction. Now, introduce a strong magnetic field perpendicular to the strip. The electrons experience a sideways force, leading to the accumulation of charge on one side of the strip. This charge buildup creates a Hall voltage, an effect explained by the Lorentz force, which dictates how charged particles move in electromagnetic fields. The Hall effect can be understood in terms of the conductivity of the material, which describes how current flows in response to an applied voltage. In the presence of a magnetic field, a current in one direction also induces an electric field in the perpendicular direction, a signature of the Hall effect. The Drude model provides a classical framework for understanding charge transport in metals by treating electrons as classical particles undergoing random collisions. It assumes that between collisions, electrons move freely under the influence of external forces, such as electric and magnetic fields, while scattering events occur with an average relaxation time tau. This leads to the Drude conductivity, which describes how current responds to an applied electric field. When a magnetic field is introduced, the model predicts the Hall effect, where charge carriers experience a transverse force, giving rise to a measurable Hall voltage. Despite its simplicity, the Drude model captures essential transport properties and serves as a bridge between classical and quantum descriptions of electronic motion. Electrons in a magnetic field, Landau levels. At low temperatures and high magnetic fields, classical physics no longer applies. Instead of continuous energy states, electron motion becomes quantized, forming discrete levels, what we now call Landau levels. To derive these quantized levels, we first analyze the dynamical variables of the system. The classical momentum of an electron in an electromagnetic field is modified by the presence of a vector potential, leading to the distinction between canonical momentum and mechanical momentum. The canonical momentum is expressed in terms of the standard Hamiltonian formalism, while the mechanical momentum, which determines physical motion, includes the effects of the electromagnetic potential. The key insight comes from the Poisson brackets of these variables. While the canonical momenta obey the usual commutation relations, the mechanical momenta acquire a non-trivial structure due to the presence of the magnetic field. This is a crucial signal that the system behaves like a harmonic oscillator, but in a modified phase space. The next step is to promote these Poisson brackets to quantum commutators. This transition follows from the standard canonical quantization procedure, where classical observables become operators. The algebraic structure that emerges is reminiscent of the quantum harmonic oscillator, with creation and annihilation operators governing the energy spectrum. From this algebraic framework, we obtain the Landau energy levels, which form a discrete, evenly spaced spectrum dictated by the cyclotron frequency. While their structure resembles that of a quantum harmonic oscillator, a key distinction lies in the high degeneracy of these levels, an inherent feature arising from gauge invariance. This degeneracy reflects the fundamental quantization of circular electron motion in a magnetic field. Crucially, the derivation underscores the deep role of gauge symmetry, ensuring that despite different choices of the vector potential, the final physical outcomes remain unchanged. Integer and fractional quantum Hall effect, topology, gauge theory, and black holes. One of the most striking features of the quantum Hall effect is the exact quantization of the Hall resistance. This effect is not merely a consequence of quantum mechanics, it is deeply tied to topology. Unlike ordinary phase transitions, which depend on local properties like temperature and pressure, the quantum Hall effect arises from the global, topological structure of the system. This means that the quantized Hall conductivity is immune to impurities and disorder, making it one of the most stable quantum effects ever observed. Physicists soon discovered something even more bizarre. Under certain conditions, the Hall resistance does not follow simple integer values, but instead appears at fractional values. This discovery led to the realization that electrons in these materials were forming entirely new states of matter, governed by a phenomenon known as fractionalization. In these fractional states, the fundamental charge carriers are no longer individual electrons, but quasi-particles that behave in truly exotic ways. These particles, called anyons, do not obey the familiar rules of fermions or bosons. Instead, when two anyons are exchanged, their wave function acquires a fractional phase, an effect deeply tied to non-commutative geometry and Chern-Simons theory. This discovery had profound implications. Not only did it deepen our understanding of quantum matter, but it also laid the foundation for topological quantum computing, an approach that seeks to use anyons to build fault-tolerant quantum computers. The importance of the quantum Hall effect extends beyond condensed matter physics. It plays a key role in lattice gauge theory, which is widely used in high-energy physics to study quantum field theories on a discrete space-time lattice. In particular, the quantum Hall effect provides a real-world example of topological field theories, which are essential for understanding gauge invariance and quantum anomalies. In lattice gauge theory, the quantum Hall effect offers also valuable insights into the mechanism of quark confinement. Research indicates that the topological characteristics of the fractional quantum Hall effect mirror the confinement phenomena observed in quantum chromodynamics, QCD. Specifically, the topology of a three-quark color singlet system in QCD has been found to be equivalent to that of the fractional quantum Hall effect with a filling factor of 1/3. This suggests that the quark confinement mechanism in QCD can be understood through the topological framework of the fractional quantum Hall effect, providing a novel perspective on confinement as a correlation effect. But its implications go even further into the physics of black holes and holography. There are striking parallels between the edge states in quantum Hall systems and the behavior of fields near black hole horizons. Just as the quantum Hall effect describes a gapless edge mode surrounding a gapped bulk, black hole physics describes a horizon with associated quantum states. The mathematics of the quantum Hall effect also resembles Chern-Simons gauge theory, which appears in string theory and the Badis-CFT correspondence. In holography, certain gravitational theories in anti-de Sitter space correspond to quantum field theories living on their boundaries, much like the edge modes in quantum Hall systems mirroring bulk physics. These insights suggest that the emergence of space and time in quantum gravity may share deep connections with the topology of quantum materials. Conclusion. The quantum Hall effect is more than just an exotic phenomenon in condensed matter physics. It is a macroscopic quantum effect, deeply rooted in topology, gauge theories, and fundamental physics. Its implications stretch far beyond materials science, influencing fields as diverse as quantum computation, black hole physics, and high-energy theory. This remarkable effect reminds us that quantum physics is not limited to the microscopic world. It can manifest in ways that challenge our deepest understanding of reality. If you enjoyed this lecture, subscribe to Quantum for more explorations into the mathematics and philosophy of quantum mechanics. Thank you for watching.